Welcome everyone to another learning session. Today we are going to discuss about systems design fundamentals. We are not going to do any systems design yet. Before even we do systems design, we need to prepare or learn some essential fundamental topics. Only after that you can really do systems design with all these components. Otherwise, you'll be trying to do certain things that you think are right, and you may end up in a problem or situation called as golden hammer problem. How many of you know about this problem or situation called golden hammer problem? Golden hammer problem says that if only what I have is a hammer, whatever is there in front of me will look like a nail. It means that if I know only certain components of systems, or if I know only certain concepts or characteristics or existing systems, then I will tend to put all of my design from the perspective of those little things I know. And for that reason, an architect should not only have a depth of knowledge in certain areas, but also should have breadth of knowledge in all other areas. That is why I start all of my architect sessions like AWS architect session or Azure architect session with systems design. And once you have the knowledge of systems, once you know the components, it is only about mapping this knowledge to whatever is there on either AWS cloud or Azure cloud. I have more than 6 years of experience as a cloud architect. And during this time, I have worked with both AWS cloud as well as Azure cloud. Ultimately, behind the scenes, everything is design concepts. So once you learn this, you will be in a better position to become an architect either in AWS track or in Azure track or GCP track or whatever track you want to choose. And this session will only be useful if you are very seriously participating in it, not by listening, by actually answering the questions from what you think is correct. In systems design or in preparing architectures, there is not always a single correct answer. You may have to make trade-offs, and you may have to take decisions based on those trade-offs. And some of the things that we will learn, like the characteristics and all, will help you take that trade-off based decision. It is all dependent on how much knowledge you have. It does not matter if you have expert knowledge in a topic or not. At least you should be knowing, okay, that thing is there. So when you get a problem, you can ask yourself, okay, will that concept fit here? I don't know, but it is worth giving a look into that also. If you don't know that a thing is existing at all, then you will think that, okay, this is what I know, then I'm going to do it in this way only. So please be open and always make sure you have both the depth of knowledge as well as breadth of knowledge. Through this systems design class, I will try to increase your breadth of knowledge, and based on your request, I will go deeper into almost all of these topics in coming days. But the priority will be based on what you request for. Systems design fundamentals 101 part 1. This is kind of a big topic. So I have split it into 4 parts. And in this tech series, we will look into almost everything you need to get started with systems design. In this series, we are not going to do systems design, but we are going to learn everything that is needed to do systems design. And in phase 2, we'll be actually doing systems design. And in phase 2, actually you will be doing, and I'll be there with you. We may be doing it in a mock interview mode, or we may be doing it in a team mode where teammates will be sitting together, and then you'll be architecting with the feedback from other people. In either the interview mode or the team mode, I'll not be able to handle a lot of people at the same time. And hence, I'll be selecting people from this series based on your participation. And if you are watching this later in YouTube, you can participate there also by making comments, by answering the questions I ask. And also, if you are watching from any such platforms, please feel free to pause and then answer, and then unpause and then continue. What we will learn. As I mentioned, I have split it into 4 parts. Part 1, fundamental concepts like protocols, client-server model, networking concepts, etc. And also data concepts. Most of the concepts that are needed for an effective systems design. And part 2 are the characteristics of systems, the good to have features like availability, scalability, etc. And part 3 consists of concepts that influence the characteristics, such as replication. If you do replication, then you can increase your availability. And part 4 will be learning about some components of systems design like load balancers, application gateways, caching, and also some useful tools that are already existing that you can reuse in your systems design. So if you have all these things with you, then you are in a very good situation to do systems design with confidence. If you look into a doctor who is going to do an operation, so he will be having all those things ready, and there will be people who are waiting to give him those things while he does the operation, right? So similarly, you should have all these things. Imagine the doctor going back and then picking things or not having the right equipment for doing that particular operation. You may be thinking, okay, that is operation which is very serious and this is just systems design. But if you are in a job interview for a job that you consider your dream job, then it is as same as doing an operation, because you may not be getting a second chance. And even at work also, everything that you say or do creates an impression of yourself in front of others. And that impression is really important for you to climb up the ladder. A quick disclaimer. We will learn a lot of important topics at high level that can help in designing systems. You will have to dig deeper into topics based on additional materials provided or by attending or referring to additional 101 sessions. Links to additional materials will be added in the description for the recorded video. And along with the course, I might give you some coding assignments. The coding assignments shared during session are optional, but can help you a lot in having a solid understanding of these concepts. Try to implement these concepts or a simulation of these in your language of preference. And you should check in such assignments to your own GitHub account following the JIT 101 session we had, and share links in our community groups, or you can share as comments in the YouTube or whatever portal you are watching it. Part 1, fundamental concepts. So here we will start with why learn system design fundamentals and the difference between high level design and low level design and all. Then we will look into some important concepts such as the essential networking concepts to start with, the OSI model, TCP IP model, packets, datagrams, TCP, UDP, HTTP, etc. I assume most of you may have attended the Azure Networking 101 session. If not, do at least watch its recording. Then we will look into something which is very important and sometimes tricky for people, encryption essentials. We will see about symmetric encryption and asymmetric encryption. We will also see how HTTPS work behind the scenes. And finally, we will conclude discussing about essential storage and database concepts. In case if you are new to my sessions, I am Hartin Kaniguthotu. I am an author architect. I like to teach, and I am also a Microsoft certified trainer. You can know all about me by going to this link, hartin.github.io. So why learn design fundamentals? Just like you need to have knowledge of data structures to design good algorithms, you need a systems design fundamentals knowledge to design good systems. Whenever you go for a coding interview, you'll be given a problem to solve. And when you solve that problem, you will be using a lot of data structures such as stacks or queues or linked lists or arrays or strings or tries. So if you have that knowledge, then you will be able to solve a lot of those problem solving coding questions. High level design versus low level design. High level design is the general systems design. HLD refers to the overall system architecture at a macro level. Low level design details HLD at a micro level with the component level design, including class diagrams, pseudocode, etc. While high level design is created by solutions architects in general, low level design is created by designers or developers. Whenever you start your career, and if you are in a developer role, you'll be mostly focusing on low-level designs. Even in your interviews or discussions also, you'll be getting questions on low-level design. But as you grow up, you will be discussing more on the architecture level or high-level design. And then you will be passing on those high-level designs to other developers who will be actually working on the low-level design part. In our systems design discussion, can you guess whether we will be discussing high-level design or low-level design more? Okay, it will be high level. Essential networking concepts. We will quickly look into what are these packets, datagrams, protocols such as TCP, UDP, IP, HTTP, and also some models such as OSI model, TCP model, client-server model, peer-to-peer models, etc. These may or may not be very important for you, but a few things are important, and I will surely tell you to focus more on those few topics. Packet switching is the grouping of data that is transmitted over a digital network into packets. So packets are made up of header and payload. Data in the header is used by networking hardware to direct the packet to its destination, where the payload is extracted and used by the application software. A datagram is the basic transfer unit associated with the packet switch network. A datagram may be considered as a packet without a TCP header and represent the packet sent in UDP. How many of you understood what I just read from these two paragraphs? Almost nothing, right? So basically, all of you may be knowing behind the scenes, data is represented as zeros or ones. And these zeros or ones are actually transmitted through the wire as electronic signals, like a positive voltage, zero voltage, or negative voltage, in a way that the average is zero. But you don't have to worry about those things. Bits, these zeros and ones, are grouped, something called as packets, and these can be used in the transmission protocols or transport protocols such as TCP and UDP. So UDP is a protocol which is faster, and at the same time, it does not care about reliability or guarantee. So you just send and hope that it will reach its destination. But TCP is a protocol that has more guarantees. It will have additional data that will make sure, okay, this data has been successfully delivered. So transmission control protocol, or TCP. So TCP is a connection-oriented protocol. The communication parties should establish a connection before transmitting data. TCP is reliable as it guarantees the delivery of data. Created on top of the IP protocol, which we will see now. Packets will now have the TCP header also. So TCP is a transmission layer protocol. We will see which are the layers shortly. So TCP is a transmission layer protocol used by application layer protocols such as HTTP, HTTPS, FTP, SMTP, and Telnet. So you may not be working a lot on the other layers except transmission layer and application layer. So if you are working on cloud, you will be mostly working with two layers, the layer 4 and the layer 7, which we will see shortly. So user datagram protocol, it is a datagram oriented protocol. There is no overhead for opening a connection, maintaining a connection, terminating a connection. The delivery of data cannot be guaranteed though. UDP is efficient for broadcast and multicast type of network transmission. UDP is a transmission layer protocol like TCP. And this is used by application layer protocols such as DNS, DHCP, TFTP, SNMP, RIP, and voice over IP. So I still remember in my college days, in my pre-final year, we had designed a chat system using UDP. Internet protocol, network layer protocol that deliver packets from the source host to destination host based on IP addresses in the packet headers. So every computer in a network or even the World Wide Web Internet have an IP address. So this IP address will tell you where to go. It is just like your home address. So this IP address will look like something that you see here, 192.0.2.1 or this 2001:DB8, . But it is difficult to remember these numbers, right? So that is why we have domain names. You may have seen domain names like google.com or trainso.com or cloudrx.com. Behind the scenes, these domain names are associated with some IP addresses. And there is this system called a domain name system or DNS that help translate these domain names into IP addresses and vice versa. And there are two types of IP addresses, IPv4 and IPv6. IPv4 is 32-bit. It is almost getting extinct. So there are not a lot of ones pending. That is why we have started using IPv6, which is 128 bits. And I don't think it will get used up in near future. And these IP addresses, we can represent them using a notation called as a Cdr notation. And it's very useful whenever we are working on concepts related to networking on cloud or on-premise. Cdr notation is a representation of an IP address where the suffix represents the network or subnet the IP belongs to. Okay, so if you see this 192.0.2.1/8, this 8 means that 8 bits out of the total 32 bits are used for finding the network or subnet. Subnet is a subnetwork within a network. So you can divide a network into different subnets to actually give those subnets different permissions. This /8 denotes the number of bits that are used to find that network or subnet. So tell me, if I have a /8 network or a /16 network, which is big, which can handle more IP addresses. Okay, it is a /8, right? Because you will get a 32 minus 8 bits to create your IP addresses. And with a /16, you get only 32 minus 16 bits to create your IP addresses. And there are also some IP addresses within a network and subnet which are not usable. We will not look into those things now. We will see them whenever we are working with a cloud or networking in general. HTTP. So HTTP is an application layer protocol. In the OSI model, as we will see in the next slide, there are a lot of layers. And in the TCP IP model also, there are layers. In both of these, you have application layer and a transport layer. And this application layer is not actually the apps or applications that you come across, but the protocols that support those applications. Can you tell me, a web browser, is it part of application layer or not? No. When you hear this term application layer, you may feel like, okay, this is a part of the application layer, but HTTP and HTTPS, the protocols that are supporting this web browser are part of the application layer. When you consider HTTP as a protocol, supports your web browsers. HTTP protocol specifies guidelines for communicating with a server. When a client makes a request to a server, it can use some HTTP methods to tell the server what it needs. For example, if you use a get, it will tell the server that I need to get certain things. If I use post, I'll be telling the server that I need to create certain things. If I use put, I can tell the server that I need to update certain things. Delete is for delete. Similarly, I have patch for partial updates, and I have options. So how many of you have heard about this term called CRUD, C-R-U-D, CRUD operations? So CRUD or CRUD means create, read, update, delete. So you can implement CRUD operations with HTTP. So generally for create, it is post. Some people may use put, but post is more accurate in my opinion. Then you have put for update, get for read, delete for delete, and so on. With HTTP protocol, you use HTTP methods to connect with a server. How does the server connect with you back? So server connect with you using HTTP response codes. So these response codes include numbers starting with 1, starting with 2, starting with 3, starting with 4, starting with 5. So the ones starting with 1 are generally informational. The ones starting with 2 are generally success messages. The ones starting with 3 are generally redirect messages. Ones starting with 4 are generally client errors. So like 404, you may have seen a lot of times, right? And the ones starting with 5 are actually server related. For example, the 500, which says that the server doesn't have any clue about what has happened, but it has gone wrong. So if you go to this top right corner of your browser and then go down to more tools and then go to developer tools, you can see developer tools. Then if you go to this network section and try to run any URL, google.com or whatever URL you want, then you can see a lot of things happening behind the scenes. Okay, so see, whenever I clicked on this, what happened? So this response came, and what were the headers? So the request method was get. So from the browser, I made a get request. So basically, when I do anything by default, it will be a get request. And what was the status code back from server? It was 200. So it was a HTTP get method, and the response was status code 200. And then a lot of other headers also, which you can explore today as a homework. So hope you got an idea about how HTTP work behind the scenes. So now we will look into the OSI model or Open Systems Interconnection model. So this is a reference model. When you map things, it may map to only a few of these or more than one of these. The physical layer, this is the layer where all your physical things such as media, signal, the binary transmission will happen. Then you have a data link layer where you have the MAC and LLC, which does the physical addressing. So then you have the network layer, which does the logical addressing of things. Then you have transport layer, which is an important layer for you, where all the end-to-end connections and transmissions happen. The important protocols are TCP and UDP. Then you have the sessions layer. It establishes, maintains, and tears down session. Then you have presentation layer where you do things such as data compression, encryption, etc. Finally, you have the application layer where you have protocols such as HTTP, HTTPS, etc. From a design perspective or a systems design perspective, which of these layers are the most important? The fourth and the seventh. Fourth is transport layer, and seventh is the application layer. Sometimes you may be designing components and then you will be thinking whether I should put this component in layer 4 or should I put it in layer 7. So components such as load balancers, application gateways, and all these things. When we design, we will have to look into these different layers. So whenever we are in a layer such as application layer, we will have more information such as your HTTP information about the URLs, which is not available with your transport layer. So if you want to route certain things based on URL information, then you will have to choose application layer. So you are free to learn and explore other layers. But at least these two layers, transport layer and application layer, are very important from a systems design perspective. Then we have a TCP/IP model, which is a concise version of the OSI model. It has the following layers. We have the application layer, we have the transport layer, we have the internet layer, and we have also a network access layer. From a systems design perspective, application layer and transport layer are important. And when you consider some real architecture models, then you have a client server model or your request response model, where your client will send a request, like the one we saw from browser, and server responds back with a response. And we may use a protocol such as HTTP, HTTPS, TCP, etc. for this request response pattern. Okay, so Power has come back for a small visit. So one quick assignment: if you are a Java or .NET or any programming language expert or even a programming language student, create a simple client-server application. You should have a client that will send some message to a server, and server should print it in its console and then respond back, and the client can print the response in its console. If you are doing it using Java, then you can use classes such as socket, server socket, and all. Try to do it and share it in our groups. So this is another model, peer-to-peer network model. So peer-to-peer network is a distributed application architecture that partitions tasks or workloads between peers. So each peer simultaneously function both as clients and servers to other nodes on the network. Peer-to-peer networks can help speed up distributing large files to many systems. The large files are split into small chunks, and chunks are shared to peers. Peers can then coordinate with each other to get their missing chunks. So basically, imagine that you have a very big file, and then you need to give it to a lot of people, maybe all members of our CloudRix community. One way is to allow everybody to download directly from cloudrix.com. In that case, considering that we have close to 100,000 members, the cloudrix.com server may definitely come down. So what can we do? So we can split these a big file into smaller pieces, and then can give them to some of these people. And these people can then coordinate with each other and then get all the missing pieces and then connect them together. So imagine that I have split it into 10 chunks. Some of you got 1, some of you got 2, some of you got 3, so on. So when you communicate with other people, you will tell that, okay, I have 1, I need the rest. So the other person will say, okay, I have 2 and I need rest. And so similarly, you will be talking to a lot of people and eventually you will be getting all parts of the file. So protocols such as BitTorrent is very popular. Kraken is a P2P based Docker registry designed for scalability and availability. Now comes one of the most important topics, encryption. Whatever text you see here are all in English, right? You can call this plain text. Encryption is a process through which you will transform this into some other form which you cannot directly read like this one. And that other form is generally referred to as a ciphertext. And you use another process called decryption to bring back the plain text from ciphertext. So the plain text is converted to a ciphertext through encryption, and the ciphertext is converted back to plain text through decryption. When I was a kid, without knowing anything about computer science, we used to do a little bit of encryption, decryption, and all. Last day, I was watching my daughter play with her friend. Both of them were communicating with each other through a kind of encryption. So basically, they were converting each of the alphabet into an alphabet 2 or 3 times ahead of it. For example, instead of A, they will write C. Instead of C, they will write E, and so on. And when they receive the letter, they will convert C with A, E with C, and so on. That is also a form of encryption and decryption, right? And in today's world, one difference is the algorithms that are used to do encryption and decryption are kind of popular. So when kids were playing, only people who knows about this encryption and decryption methodology were those kids only. But in our case, we have a very good algorithms, and these algorithms are all published. So everybody knows about these algorithms. So if you encrypt using an algorithm, anybody can encrypt and decrypt that message, right? That is why in computer science, we also use something called as a key for encryption and decryption. So this key will be known only by two systems that are communicating. So as long as nobody else knows the key, your encryption and decryption are safe. So consider a real world example from an older era where these mobile phones or emails or internet was not present. So how do you use to communicate during those times? It was through letters, right? Imagine that one of the beautiful princess wanted to send a letter to one of the handsome prince. Some kids or somebody else will be carrying that letter, and they want the contents of the letter to be secret. One way is they can use some letter replacing encryption or decryption that we were using before, but somehow they have to communicate this thing with the other person, right? So these two people who are communicating will need to communicate the letter replacing logic or the encryption and decryption methods with each other. So can they write these things also and send to the other person that from next letter I'll be using a letter replacing 2 characters ahead or 3 characters ahead? Then people who are carrying will also get to know the logic, and then they will be also doing encryption and decryption, right? So in real world also, if two people or two systems are communicating using encryption and decryption and uses only one key, which is also called as a symmetric encryption, then how do you transfer the key? How do you share the key between each other? If you send the key first, then similar to our kingdom example, people who are carrying or people who are standing in the middle may get the key. So this is also called as man in the middle attack. So that is why engineers have come up with asymmetric encryption, which uses 2 keys. Okay, in symmetric encryption, you have only one key that is used for encryption and decryption. And AES is a popular symmetric key algorithm. And with asymmetric keys, you have two keys. With symmetric keys, you have a combination of public and private key pairs. So pair means two, right? So everybody will have a pair of keys. One is called a private key and one is called public key. Private key is something that they will hold with themselves, and public key is something that we will share with the world or share with the other person. And with asymmetric encryption, you can encrypt using one key and you can decrypt using the other one in the pair. For example, if you are encrypting using the public key in a pair, you can decrypt using the private key in that pair. If you are encrypting using public key in that pair, you can decrypt using private key in that pair, and vice versa. Before we proceed, let me ask you one thing. How many of you know and understand these terms called confidentiality and integrity? Confidentiality means if I want to send a message to somebody, nobody else should be able to read it. Integrity means when I send a message, the recipient should be sure that I have sent that message. Confidentiality means if I want to talk to, say, Kavya here, I will need to somehow make sure that only Kavya reads my messages. So now tell me, if I need to send a message to Kavya and I need to make sure it is confidential, meaning nobody else should read it, which key will I use to encrypt that message? There are four options. Hartin's public key, Hartin's private key, Kavya's public key, Kavya's private key. Everybody should answer. Otherwise, you will not get the invite for next session. If you don't know, just make a guess. My goal is confidentiality here. I need to make sure that only Kavya should read the message. Nobody in the middle should be able to read it. So let me take one by one. Let us take the first one, Hartin's public key. So here I am sending a message to Kavya, and the only person who should read should be Kavya. So if I encrypt any message using Hartin's public key, which is the only key that can decrypt that message? Hartin's private key, right? And will Hartin give away his private key to anybody? No. So definitely Hartin's public key is not the answer. Because you should not be giving your private key to anybody. So now let me go to Hartin's private key. So if I encrypt using Hartin's private key, who can read that message? The whole world has my public key, right? Or they can get my public key because it is public key. So will that message be confidential? No. So Hartin's private key is also not an option. So what about Kavya's private key? Can I encrypt with Kavya's private key? No, right? I don't think Kavya will give her private key to me. She shouldn't be giving to anybody, right? So what is the only thing that is left? It is Kavya's public key. So Kavya's public key is with everybody. So I also have it. So if I encrypt using Kavya's public key, who is the only person who can decrypt it? It will be Kavya. So now let me ask you another question to make sure you have really understood these things. Now my goals have changed, or our goals have changed. So I am sending a lot of messages, and Kavya is having doubt that whether these messages are actually sent by Hartin or not. Now we don't care whether the world is seeing or reading these messages, but Kavya wants to be sure that the message is sent by Hartin only. So with which key will I encrypt now? So again, same options: Hartin's public key, Hartin's private key, Kavya's public key, Kavya's private key. As the goal is integrity, and Kavya needs to be sure that this message is coming from Hartin. It is Hartin's private key, right? Who is the only person who has Hartin's private key? It is Hartin. So if somebody is able to decrypt that message using Hartin's public key, then they can be sure that, okay, this message was created by Hartin only. So this concept can be used in digital signatures and all. And you may be also using a combination of these two keys for getting both confidentiality and integrity. We are not going to go deeper into this subject more, but at least if somebody asks you what this encryption is, or what this decryption is, what symmetric encryption is, and what asymmetric encryption is, and how this public-private key pair work, will you be able to answer? So now we will look into HTTPS. We saw what HTTP is, right? So HTTP can be attacked and people can get the message, and it does not make that a secure approach. So problem with HTTP is a man-in-the-middle attack that we discussed using our kingdom example. It is based on TLS protocol. It's a newer version of SSL. TLS handshake happens between this client and server. And TLS handshake also uses SSL certificate signed by certificate authority using its private key. Don't worry if you have not understood all these things. We will see them in bit more detail now. So HTTPS uses TLS, and TLS has a handshake mechanism. So how does TLS make sure that the communication between two parties, let us say a client, browser, and server, are secure? The S in HTTPS stands for secure, right? One option was to use a public key, private key combination like we discussed earlier. But tell me one thing from the previous slide. Which of these is faster, symmetric encryption or asymmetric encryption? It is symmetric encryption. Symmetric encryption is faster than asymmetric encryption. So which one should we prefer, symmetric or asymmetric, when we have a chance? A faster one or a slower one? Faster one, right? Whenever you have a chance, you should go with the faster one. So which is the faster one? Symmetric. For your communication over internet or our kingdom example, they can definitely communicate with the symmetric encryption without any problem. What was the only problem that we faced? It was about exchanging the key, right? So if two people know the key already, then they can use a symmetric encryption to communicate between each other, right? After sharing the key securely, even if you use a symmetric encryption or even if you use asymmetric encryption, you will have a confidentiality, you will have integrity, because only you two have this key. Clear until now? This knowledge is essential for understanding HTTPS. In summary, if you can somehow share the key securely, then you can use that key to do a symmetric encryption, which is much faster than asymmetric encryption. You should always look for better performance when you have a chance. Sometimes you'll have to make a trade-off between performance and security. That is another story. But here, if you have already shared the key securely, then you can decide whether to go for symmetric or asymmetric. Both will work. But symmetric is preferred because it is faster. So considering all these things, how does a TLS handshake work? So when a client communicates to server for first time, client sends a client hello. So when a client sends hello, it will create and send a random number. And then server will send back a hello, sending server's public key with an SSL certificate. Forget about SSL certificate for time being. So client sends a hello to server with a random number, and the server sends a hello back to client with another random number, and then with the server's public key inside a SSL certificate. And then client will now send a secret called as pre-master secret. This time client will encrypt using server's public key. So who is the only person who will be able to decrypt it? It will be the server. So the client and server uses the pre-master secret because client generated and sent to server, right? So both client and server has all this information. It has all these random numbers, and most importantly, it has these pre-master secret. So both client and server has pre-master secret, and they will use this to generate a session ID. So this session ID further can be used as a symmetric key for the current session. And as a final step, server and client sends an encrypted message to each other using this session ID to finish the handshake process. In summary, server and client uses asymmetric encryption to create a key that is then used for communication using symmetric encryption. Does it make sense? There are variations of this, but from a systems design perspective, this knowledge is enough. If you are working in a security field, you can definitely explore more. So we left one topic from this slide, which was SSL certificate. Imagine that the client is sending hello to server, and server is directly sending server's public key. What if man in the middle attack happens and somebody else captures server's public key and replaces it with their own public key? Client will think that, okay, I have got server's public key. And then client will encrypt using middleman's public key, thinking it is server's public key. So who can read those messages? Man in the middle or the server? Man in the middle, right? So there should be a way for client to be sure that whatever I have received as server's public key is actually server's public key. So somebody with authority has to certify that this public key belongs to this server, and this is a valid public key. And there are many such certification authorities. So as an assignment, you can find out popular certification authorities and share it as a comment. For the purposes of testing, you can also assign certificates, and that is called as a self-signed certificates. But you will get a warning that, okay, these are self-signed, these are not coming from a certification authority. Clear? We will have other one-on-one sessions for networking, IP addresses, cyber security, etc. Essential storage concepts. When you work with systems design, you will definitely have to decide on the database also. So you need to understand what are the different options you have, at least from a high level. So what is a database? It is an organized collection of data stored and accessed electronically from a computer system. The important point here is that it is an organized collection of data. So can you name some of the popular databases? Oracle database, MySQL, Postgre, Sybase. And then database management systems. They are a software that interacts with end users, applications, and database to capture and analyze data. So basically, it manages the database. So you have a database, which is an organized collection of data. And then you have a database management systems, which basically manages that database. And when you consider storage from a systems design perspective, you have to think about disk versus memory. Whether you will be storing data in your hard disk, or whether you will be loading that into memory or your RAM and then you process it. Which is faster, processing it from hard disk or processing it from RAM? Is RAM or memory, right? And again, from the hard disk perspective, you also have different kinds of hard disk. You have your traditional hard disk drive, or you have the newer SSDs. And even within SSDs, you have ones with higher performance, medium performance. You have a lot of options to choose from. And whenever you make a decision between your disk and memory, one of the things that you should ask yourself is about performance, and the other thing should be persistence. A relational database is a digital database based on relational model of data. Relation represents a table as per mathematics, but in general, it is used to represent relationship between tables in case of relational databases. A software system used to maintain relational databases is a relational database management system. And most relational databases use SQL or structured query language for querying and maintaining the database. And in general, most relational databases follow ACID properties: atomicity, consistency, isolation, and durability. All of these are needed for something called as transactions. So what is a transaction? So for example, if you are transferring money from your bank account to another bank account. So if I am transferring money from my account to Amarnath's account, so what all things should happen? The money should reduce from my account. It should be added to his account. There will be a series of things that needs to happen together. If one of those do not happen, the other also should not happen. As an assignment, you can explore more on atomicity, consistency, isolation, and durability. We will also discuss more about them in our databases 101 or relational databases 101 session. NoSQL. Initially, it was used to refer to databases that did not use SQL. And then people started calling it as not only SQL, because some of these NoSQL databases also support some kind of query language. So stands for not only SQL now. And unlike relational databases, here you will have multiple options. NoSQL is not just one kind of database like the relational databases. So there are different categories. You have a category called key value store. A popular example is Redis. You have categories such as document based. A popular example is MongoDB. You have blob store. You have columnar store. Columnar store. You have Cassandra. Blob store or object store. You have Amazon S3 or your blob storage on Azure Cloud. Then you have time series databases. You have graph databases. There are a lot of different categories. And based on your use case, you will choose one. For example, if I want to build something like Facebook, where my connections and their connections are important, I might go with a graph database. So based on use case, you should be able to choose the right database. Or first, you can choose the right database category, and based on what you have available on your particular cloud of choice or from your available list of approved software within your company, you can choose them. Many of these categories may have more than one databases under them. So similar to ACID, here they follow something called as base, which is basically available soft state eventual consistency. Out of this, eventual consistency is a key term. Data may be replicated across multiple systems or partitions. In strong consistency, every replica will be having the same version of data. But in eventual consistency, the data is replicated asynchronously, and eventually all replicas will have a same version of data. Why do you need multiple systems or multiple partitions? So that is for better availability. What if one server goes down? You'll have others to work, right? Actually, most of these becomes important, especially with respect to distributed systems. When you have a distributed system, you will have data replicated across multiple systems. And then whenever you are writing data to one system, you need to replicate it. In most consistent models, what they do is they do synchronous replication. What do you mean by a synchronous and asynchronous replication? Synchronous means if I am writing to, say, system 1, it will write to system 2 also, and then it will tell me that, okay, the write is complete. Asynchronous means I write to system 1, it will tell me, okay, it is written to system 1, and then after that, it will talk to system 2 and then give the information. So whenever performance is important or availability is important, I can go with asynchronous based writing. And if consistency is important, I can go with synchronous itself. So always as an architect, you will have to work based on trade-offs. How many of you have heard about this concept called as CAP theorem? CAP theorem is one of the most important theorems proposed with respect to databases working in a distributed environment. Okay, before going to CAP theorem, here is your assignment number 3. List popular relational databases and also list popular non-relational databases belonging to each category is listed. So find out as much as possible databases that belong to each of these categories, and you can answer them as comments in the YouTube channel. So now coming back to CAP theorem, it states that it is impossible for a distributed data store to simultaneously provide more than 2 of the following: consistency, availability, and partition tolerance. CAP theorem says that you cannot have both consistency and availability when a network partition or failure happens. When a network partition failure happens, should we decide to either cancel the operation and thus decrease availability but ensure consistency, or proceed with the operation and thus provide availability but risk inconsistency? Imagine that I have system 1 and I have system 2. System 2 is a replica of system 1, and I am writing to system 1, and then this system 1 is writing to system 2. In case of a consistent approach, I will write to S1, and then S1 will write to S2, S2 will confirm, and then it will confirm me that everything is fine. In an availability based approach, I will just write, and S1 will tell me back, okay, it is written to S1, and then it will do these things. The first approach is a consistent approach, and second approach is a availability approach, which is also called as, we learned a term, right? Eventual consistency. So eventual consistency means if somebody else read, they can see a different answer. Okay, now when I am writing to S1, what if there is a network failure? So the partition tolerance refers to how tolerant is your system with respect to network failure, right? So when a network failure happens, what are the 2 things I can do? Okay, so failover is different. Failover happens when a system goes down. When S1 goes down, S2 will become primary. That is failover. But here, the network is not working. So S1 has no way to communicate to S2. So if I am sending data, there are 2 things S1 can do. Either S1 can write data to S1 and tell me that, okay, I have written. This data will be available. And when S2 comes up, eventually this can be written. But until this is fixed, S2 will have a different version of this data. Or it may not have this data at all. Data is available here, but not consistent. And what is the other approach I can take? I can say that, okay, I am designed for consistency. So I will not write this data and make it different from S2. So I will fail. So here data in S1 and S2 will be consistent with each other, but it will not be available. The new data will not be available, or the system will not be available for writes. So once again, CAP theorem states that it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees: consistency, availability, and partition tolerance. CAP is frequently understood as if one must choose to always abandon one of these 3. In fact, the choice is really between consistency and availability, and that too only when a network partition or failure happens. When a network partition or failure happens, should we decide to either cancel the operation and thus decrease the availability but ensure consistency, or proceed with the operation and thus provide availability but risk inconsistency? And this is important whenever you are working with distributed systems. If everything is running on one system, it does not make much sense, right? We will explore more in sessions such as storage 101, databases 101. Based on your interest areas, you can explore more. Or if you want me to take a session on any of these in a much more detailed way, you can suggest as comments. So part 2, we will not discuss today, don't worry. In part 2, we will be discussing a lot about the characteristics of systems like availability, scalability, etc. There is a question, if partition tolerance is there, then consistency and availability will also be available. This partition tolerance, it is a bit confusing for some people because they think it is when systems are partitioned into different partitions. Partition tolerance basically means if there is a partition. What do you mean by partition? A failure in the network. How will a system handle it? So you have replicas. And what happens if a partition happens in that network? Without a network, you cannot have consistency, right? So then you'll have to choose between consistency and availability. When I learned initially, I used to ask myself, why can't these three be together? Then I also saw some videos. And then when I started working with distributed systems, things became more clear. At least you have got some idea, right? So tell me one thing, was the session useful? Have you learned anything new today? If you have learned anything new, then all the challenges I had to face with respect to power, air conditioner, everything is worth. But if you have not learned anything new, it is not worth for you or me, right? We will all learn and grow together. You can also share knowledge based on what you have learned or what you have done at your work. You can also suggest what more topics would be interesting to all of you. Please leave a comment under the video. I'll look into it. I will pick it from there and I will plan for a session for that. So sometimes even trainers will have to plan, right? So I may not be knowing everything. So certain things I'll have to learn and then present. That is why I always take sessions based on what I actually work. Because when I learn more to take a session, I'll be more productive at my work. And when I am more productive at my work and then solve a lot of challenging problems, I can be more effective at my teaching also. So that is why whenever I am working with AWS Cloud, I train people on AWS Cloud. Whenever I am working with Azure Cloud, I train people on Azure Cloud. I always want to do these two things hand in hand. Priority is always work, because that is where you get your salary to pay your EMIs and all. So based on work, I change my training plans also. Training and teaching is something that I like a lot. And the reasons I have listed in that introduction to Cloud Rigs and Train, so audio message video. So you can go through it. And we will again connect for another session soon. And I always value people who attend live and stay till the end. And also people who leave feedback, because those things actually encourage any teacher to teach more. Not only me, because I interact with a lot of other trainers also. So all of them like that. And all of these things motivate all of them also. Okay, so do leave feedback and suggest what more you need, and also come forward and take sessions, and we can all learn together and grow together. Many people have asked about career path on cloud computing. I've done that once before. I'll definitely do that in coming days. So just be active in our groups and attend regular sessions live or even the recording. Even after the recording, you can ask your doubts in our WhatsApp groups or even in YouTube. And I'll always try to get back to you as early as possible without affecting my regular work. So bye-bye for now. See you all in next session.